Welcome to solverfy.
Alright, so for this question, they have given us a diagram with 3 containers and a certain number of particles in 2 of the containers. And they're asking us, after this system reaches equilibrium, what this new diagram is going to look like. So it says that the stop clocks right here and right here are closed. So once the stop clocks are open, they're asking us what this is going to look like. So once they're opened, our number of particles of blue and black are going to stabilize throughout the 3 containers. So that's going to look like this. So we'll end up having an equal number of blue and black particles in all 3 of the containers. It says that 1 dot, or basically 1 particle, is equal to 10 to the 6 particles. And that is for blue and black. And so this is what the system would look like after the 3 containers reach equilibrium. So for part A of this question, they are asking us how many blue and black particles are going to be in container B. So for the black particles, we have 10 to the 6 plus 10 to the 6 particles because we have 2 dots. So we basically have 2 times 10 to the 6 black particles, and we'll switch colors for the blue. So we basically have the same for blue, 10 to the 6 plus 10 to the 6. So we have 2 times 10 to the 6 particles for black and blue in container B after equilibrium has been reached. For part B of this question, they're asking us this basically the same concept just for container A. So since we know that we have equal number of blue and black particles in container A and B, we know that for the black particles, we have 2 times 10 to the 6 particles. And then same for the blue, we have 2 times 10 to the 6 particles for container A. For part C of this question, they're actually asking us for the pressure of container C after equilibrium has been reached. They do give us the pressure of container C before. I'm going to label that PC1 for the first pressure. They tell us that our first pressure is 750 torr, and they want to know the pressure after equilibrium. So if we go back up to our first diagram, we see that there are basically 6 times 10 to the 6 particles in container C before we start to reach equilibrium. So to find our second pressure, we're going to take the particles of container C after equilibrium, so 4 times 10 to the 6 particles. We're going to times that by our first pressure, which is 750 torr, and we're going to divide that by the beginning number of particles in container C, which is 6 times 10 to the 6 particles. Particles will cancel out, giving us torr, so our second pressure is going to be 500 torr after equilibrium has been reached. So that is the pressure of container C. For part D, they're asking us the same thing, just with container B. So if we go back up to our first diagram, before equilibrium, there's no particles in container C, so basically the pressure is 0. But we know that container B has 4 times 10 to the 6 particles after equilibrium has been reached. So we're going to assume that particles is proportional to pressure, and if our system has already reached equilibrium, we're going to assume that our second pressure for container B is going to be equal to that of C, or container C. So our pressure is going to be 500 torr, because we're going to have the same number of particles in all 3 containers. So pressure will be consistent throughout the 3 of them, and they say that the stop stopcock volume is negligible, so we don't have to add that or subtract that to the volume of the 3 containers. So the pressure for container B after equilibrium is 500 torr.